This is session 3, maintaining quality, reliability, and durability with meeting growing demand at our Roundtables US event. Welcome back. I hope you enjoy the networking break and made meaningful connections. I'm Anne Fischer, Senior Editor of PV Magazine USA. Once again, I'd like to introduce our moderator, Jonathan Gifford, Editor-in-Chief of PV Magazine, to take us into the next session.
Hi again, Anne. Thank you very much. Well, there's little doubt that solar is undergoing a period of unprecedented expansion, particularly driven by the IRA here in the US. But the commercial incentive to deploy fast and to maximize financial returns by reducing costs and boosting power output must be balanced with long-term reliability. For solar to maintain its reputation as a reliable power source, the arrays and technologies being installed today must remain operational long into the future. The quality session of the PV Magazine Roundtables events right around the world have attempted to get to the bottom of these challenges. And with technology never standing still, there's always a lot to address. We have a panel discussion today with 4 experienced and knowledgeable experts to discuss the role of data and testing in maintaining product and project quality. But before the panel discussion, our presenter in this session is an experienced PV system designer with a strong engineering background. Prior to joining LONGi, she spent more than 5 years with Sunrun, and she volunteers with Grid Alternatives. Alyssa Huang is the Product Marketing Manager, Project Solution Department for LONGi Solar, and it's a pleasure to welcome you to Roundtables US 2023.
Yes, thank you so much, Jonathan. And yeah, with that, I'll begin with my presentation.
That would be great. Please take it away.
Yeah. Let me share my screen. All right, so today I'll be briefly introduce our lifecycle quality program and how it can ensure the long-term module reliability and performance. So beginning the presentation, I just have a brief introduction of our company. So we are LONGi Solar, and we're a global leading solar technology company. We mainly manufacturing solar wafers, cell, and modules. So our company was established back in year 2000, and now we have more than 60,000 global employees, and also 85 gigawatts of production basis. So actually, we spend a lot of our R&D fundings of our total net profits. So back in 2022, we spent almost half of our R&D investment, half of our net profit in R&D investment, which ranked top 1 among the PV module manufacturers, and which able to build a strong track record of global module shipment. So as you can see on the graph there, in 2022, we ranked top 1 for module shipment and wafer shipment. Yeah, so as the PV technology is trending toward high efficiency and high power, a module's reliability becomes more and more important to ensure the long-term operation of the PV plants and eventually the return on investment. So a lot of the operation and maintenance cases are due to equipment failures. And for PV modules, the most common module failures include glass breakage, junction box failure, cell crack, and so on. So the core idea to maximize the return on investment and lowering the LCOE is to reduce unpredicted module failures to reduce the life cycle cost by reducing the repair and also maximizing the total energy yield by reducing your module's yield loss and degradation. So as a module manufacturer, we need to ensure the lifecycle product quality and reliability of our products, especially against the extreme weathers. So the main way to evaluate the product reliability is via testing. So right now, the mainstream testing standard is IEC or UL testing standard. However, it does have some limitations, and it's also very difficult to validate due to the solar module's long lifespan, which lasts 25 to 30 years. So we've established our lifecycle quality program, which mainly develop and then optimize the raw material and module testing standards as a supplement to the IEC standards. And basically, it simulates a comprehensive set of real-world scenarios just to ensure the module's long-term reliability. So basically, the program was established through a failure forensic study via outdoor simulation. And then we would either optimize the current conventional standing test standards or innovate our own and then validate through mass production and then finally implement it. So as I just mentioned, so one of the most common failure of PV modules happening in the field is glass breakage. And one of the reasons is due to a hot spot induced glass failure. So the conventional way of testing a PV glass is with a small sample of glass sample, which is about like 300 by 300 millimeter. But then we optimize that testing standard by increasing the glass sample to a full-size PV glass, and also increasing the testing temperature to 200 degrees Celsius. And then we would apply like local spot heatings to different parts of the glass to just resemble the hot spot failures happening in the field. So by utilizing that optimized standard, we're able to filter out unqualified suppliers that we were unable to while using the conventional testing standard. And then we're able to successfully reduce glass failure rate. And then we are able to reduce the repair and the replacement cost happening in the field. So another common failure is cell crack. So right now, the industry's most common method to evaluate cell quality is via the 4-point bending test. However, it does pose some challenges since a lot of manufacturers or suppliers, they use different types approaches, which result in lack of standardization of this test. And it's really difficult to compare the results and raises concerns about accuracy. So we've provided a solution with our lifecycle quality program by leading the formulation of a 4-point cell bending test, which is able to accurately and efficiently screen out the high quality cells and also predict the module's mechanical loading performance at the early stage, which saves time and cost. So the test standard basically is determined based on the deformation characteristic of the cell, which is formulated suitable standards for each technical points, such as including the indentar spacing, its diameter, and its setup selection. And then we need to make sure that all of these setups are compatible with various cell sizes and the thickness. And then we also need to determine a optimal loading speed to make sure that we conduct the test as efficient as possible while still maintaining the accuracy. So by utilizing this test, we're able to successfully reduce the cell cracking rate and then also prevent mechanical failures of modules happening in the field. And then a common failure happen in the field also include a diode failure, especially if you're installing your solar modules in a hot climate, which your module's operating temperature can be really high, which it can be above 85 degrees Celsius. And then as the temperature is really high, your diode may prone to fail. And once it fails, definitely it will cause a reduced power production, and worse, it can even result in fire. So normally we use a reverse bias test standard of our diodes to test the diode quality. And then we've taken the lead in raising temperature of the diode reverse bias test to 100 degrees Celsius. And then by increasing the temperature, we're able to screen out some unqualified diodes at the raw material selection stage that are unable to withstand the high temperature. And then we're able to successfully reduce the thermal failure risk of the diodes. And then we're able to reduce the power production losses and then successfully prevent the fire from happening. So I only have a limited time to go over 3 of our optimized and innovative test standards of our raw materials, but here lists a more comprehensive list of our raw material testing standard, which covers from PV glass to junction box to cell and EVA. So actually, since we're expanding our productions into like overseas or even in the US, we need to make sure that we apply the same standard to different parts of our factories. So for example, for LONGi, we've expanded our Southeast manufacturers, and also we've built our US factory, which is a 5 gigawatts module factory in Ohio in the US, which started this year in April and expects to reach full capacity mid next year. So our main goal is to ensure that this stringent raw material testing standard as well as module testing standard are applied through all of our factories to maintain the same quality standards for all of our products being produced. So overall, as the module is trending toward higher power and efficiency, I think we do need continuous research and optimization in the raw material and module evaluation standard just to ensure like a long-term operation of the PV power plants and then eventually the return on investment. So I think we can do this through mainly two approaches. One is to standardize the process to address module failures in the field and then develop a corresponding evaluation standards. And then another is to conduct more in-depth research on potentially a scientific testing standard just to avoid overkill and minimize the test cycles and cost. Yeah, so that's basically my presentation. And if you have more questions, yeah, just feel free to reach out to me. Yeah, thank you.
Thank you very much. Alyssa Huang is the Product Marketing Manager, Project Solution Department for LONGi Solar. Thank you for providing those insights for you and joining our Roundtables US event today. Coming up next is our panel on key issues and best practices in maintaining quality across the supply chain. Stay tuned. Well, I think it's really valuable to get some insights from a major manufacturer like LONGi, and in particular, the interplay between testing and standards in product development. And while there's always an imperative to innovate and remain cost competitive in the PV industry, it does appear that in 2023, new module formats and technologies are coming onto the market at a record pace. We'll discuss the implications of this on product and project quality, durability, and reliability in our panel discussion today. And I'd like to welcome our four speakers. Teresa Barnes joins us from the National Renewable Energy Laboratory, better known as NREL. Teresa manages the PV Reliability and System Performance Group at NREL, and she is also the Principal Investigator and Director of the DuraMAT Consortium for Module Materials Research. Mark Culpepper is the General Manager of Solar at Zeitview. Mark has worked in sectors ranging from general aviation to data communications and wireless technology through to network security and distributed energy. He was formerly the CTO and GM of Global Services at SunEdison. Jester is the Managing Director of PI Berlin North America. She has more than 40 years experience in the solar, renewable energy, and electronic manufacturing industry, including working on the materials construction that helped provide the first 25-year warranties in solar. And Nicole Thompson is the Head of Data Science Property Insurance with Kilowatt Hour Analytics. Prior to joining Kilowatt Hour, Nicole worked as a data scientist at an AI company where she developed explainable industrial AI solutions with a focus on reasoning algorithms. Thank you all very much for joining and welcome to Roundtables US. Now, Teresa, I'll start with you. One of the notable developments in the PV industry over the last few years has been this wholesale adoption of bigger wafers. We're now talking about this G12 format, the M12, some people call it, this very big format wafer, and then integrating that into even bigger modules. What do you see at NREL as some of the quality implications of these large format modules?
So we see that they're, of course, very popular because they're very high energy yield, right? So people want to buy them. They can save you other costs on your system and result in lower overall costs and more energy yield. But they tend to be what we call big floppy modules, because in order to make a module very large, we have thinned down some of the components like the glass in order to reduce the weight and keep the weight at a limit that the rest of the system can handle. Because if the module is too heavy, we all worry about it being too heavy to install, but you also have issues with the tracker then having to be bulkier, or the racking then having to be more significant, the piers, all the infrastructure holding that system up. And so we are seeing a large number of these big floppy modules that are less mechanically durable than modules we have installed in the past. And in some cases, that's okay. But we have to understand that these modules have less room for error. They don't have this big design safety factor for mechanical loads that some of the smaller, more stouter, thicker modules used to have. And one of the issues we're seeing is that they're often tested to and certified to relatively low loads. So they may barely pass the IEC standard, but we're seeing and hearing rumors of early failures in the field at fairly high levels. And this is concerning. One of the big issues we're seeing is with the glass. The glass is now part of the load-bearing structure of the module because the frame is thinner and the mounting is thinner and it's closer together and it's only held in the middle by the tracker. So we've made that transition while also going to 2mm glass, which in addition to being thinner is mechanically very different because it's no longer what we call fully tempered. And tempering or fully heat treating the glass enables it to be more resistant to fracture. Like if you get a rock hit at your windshield, it's not going to break every time, or something hits your window in your house. It's not going to break every single time. Whereas if you have something that's not tempered, it is more likely to suffer damage from any kind of event and more likely for that to propagate very quickly if you have like a nick in the edge or a nick in the surface. And so we're seeing more and hearing a lot about modules that with broken glass due to these large format modules that deflect in the field and then the glass basically fails. So.
Okay, and am I right in understanding sometimes with glass modules, it can actually be a different type of glass on the front sheet and on the back sheet?
That has historically been true. When you have the 3.2mm glass on the front and you have the ultra high clarity, ultra clear, low iron glass on the front, obviously you don't need that ultra clear glass on the back. You're not worried about getting maximum transmission even with a bifacial module. But the glass on the back historically was thinner. And that was okay because the glass on the front is catching most of the blowing stuff or mechanical load and the frame was thicker. So we weren't having as many issues with that. It's that we've now gone to also having this thinner 2mm glass on the front, which is heat strengthened, but not fully tempered because you just can't temper glass below a certain thickness. You can't maintain the heat temperature differential that you need to temper it in order to do that. So now we're seeing the thinner glass on both sides. Some people will argue that that's 4mm of total glass, so it's thicker than a 3.2mm piece of glass on a back sheet. But because of the difference in the heat treatment and the ultimate fracture, I would say resilience of the glass, it's causing some issues.
Okay, thank you. Terry Jester from PI Berlin. When we're talking large format modules, what role then is there for product testing in terms of alerting us to some of these failure forms that Teresa was talking about?
Well, I think you can take the tests as stated and perhaps pass them, but what I think Teresa's describing is we need to probably go further. And when I visit our sister company, PVAL, we're both under the Kiwa brand, I see mechanical load testing and hail testing. And with these modules, you see quite a bit of deflection with the thinner glass modules. So I think you can actually see, relative to obviously different constructs, how the modules will behave with high wind load or say large hailstones. And I think some of the things that we're hearing is that perhaps the hailstone testing needs to be stepped up in regions where large hail exists. And so I don't know if that sort of portends us towards a regional series of tests, which I think would be difficult to administer, but certainly, particularly with hail, I think it behooves module manufacturers to look at what statistical sort of hailstones are regionally and see whether stepping up their own internal testing is something that should be done.
And of course, the damage might not be catastrophic in that the module is shattered and the glass has completely failed. There can be kind of failures or faults or problems inside the module as a result of wind or hail or the interplay between the two of them. Is that right, Terry?
Yes, it's stated very well. I think you will see cracking, if it is severe enough, but you don't always see the damage to the cells. So for instance, when you look with EL, or fly a drone over some of the larger arrays, you can actually see these impacts, which maybe haven't shown up in the glass yet, but you see them in the cells.
Okay, thanks for that. Let's come back to testing and some of the testing regimes and the costs of that a little bit later. Nicole, I want to come over to you next. Nicole Thompson, the head of data science at Kilowatt Hour Analytics. Terry mentioned hail events. How can these, how is our understanding of hail events and the impact that they can play in terms of the project reliability over the long term, and then also implications for things like insurance? Is that a uniform thing across the country? And what can you tell us about our understanding of hail impacts?
Yeah, for sure. I think I can echo what Teresa and Terry were saying as well, in that it's not a uniform thing across the US, right? We're seeing these modules, we're trending towards thinner and thinner glass, like we mentioned. We're seeing more sites built in the central US that experiences this larger hail. And it all ties into, what Terry was saying on the testing and how we need to further those standards, that IEC standard tests up to like 1.8 joules, which is equivalent to less than 1 inch naturally occurring hail typically. And anyone that lives in the central US, you'll see more than 1 inch hail, at least at some frequency. And so that's why like labs like RTUS and PVEL and CFV and testing these modules and quantifying the differences between 3.2 millimeter tempered glass and the 2 millimeter untempered glass, and these thin film modules that also are, untempered. I think that's really important, and that's data that we take into account in our models as far as the difference in the probability of glass breakage of these different glass thicknesses and heat treatments. And so we take that into account in our models. So we model them totally differently. And that's something that I think insurance companies are starting to look at more, because it should be reflected in your premium, your reduced risk of having visible damage, because you're choosing equipment that is resilient to the perils that you're exposed to, in this case, hail in the central US. You should see that reflected in your premiums. You shouldn't have the same premium when you're using 2 millimeter glass versus 3.2 millimeter glass in places like Northern Texas or Western Texas.
Now, we're talking a lot about glass, and obviously it's very important, but Nicole, it's not only about glass in terms of hail mitigation. There's new technologies and strategies coming out. What can you tell us about that?
Yeah, I mean, hail stow is the big one. I don't know if we can even really call it new anymore. It's been around for a while. There's some other like new cutting edge ones that I'm hearing about, like from Solar Stone. They're thinking about putting a net above the panels, or like glass, like screen protectors almost. So there are some emerging technologies, but hail stow is the big one. And like we know that when you put panels in this high degree tilt, it reduces the kinetic energy, right? And that's something that you can calculate out pretty well and get like pretty well defined, that your kinetic energy will be reduced up to, around like 70% in some cases. So that can mean the difference between surviving a hail storm that is around 3-inch hail and being totally destroyed by it, right? So it's a really important tool that the industry has to use to protect themselves against hail damages. As far as like how that translates into how we model it and how your insurance premium should reflect that, showing the difference between not having, or being fixed to like 30 degrees and 50 degrees, that's a fairly straightforward kinetic energy calculation, right? And there's definitely some uncertainties in there, but it's pretty straightforward. The harder part of quantifying the actual impact of a hail stow program is looking at the probability that you will be in that stow angle when hail shows up, right? And so that goes into, do you have a weather forecasting provider? Are you willing to stow early? Are you willing to take that production hit? It's quite minimal because it's already cloudy, right? And we have an article in the SRA that demonstrates that. But are you willing to go into stow early and often to prevent these hail damages? And those are the pieces that are a lot harder to quantify as opposed to just the angle that the panels are in. And so, and Next Tracker Hail Pro, where they're automating this and putting the decision on the asset owners of, well, do you want to stow when you have a 10% chance of 3-inch hail or a 50% chance? Like, that makes it a little bit easier to quantify and makes it easier to, make the right decisions to stow when you have a risk of hail. But these are things that we at Kilowatt Hour roll into our model, and it's stuff that needs to be taken into account when insurance premiums are being decided, because it does, if you're willing and able to stow quickly and often, that reduces your risk. And again, that should be reflected in your insurance premium, so we can start price differentiating between good site design and good site decisions versus poor decisions.
Okay, yeah, so hail stow is only good if you're willing to use it, if you're willing to stow.
Yeah, exactly.
Now, Mark Culpepper, you've been waiting patiently. I understand at Zeitview you've been carrying out a survey program. What can you tell us about what that's revealing in terms of project quality and kind of health status of projects across the US? Oh, I think you're muted.
Yeah, we call it condition state analysis, right? And what we're basically looking at is, so it's not a performance test per se, it's basically what's the condition of that asset at the time that we do that overflight. And the overflight is both thermal as well as visual. This year we did overflights on about 6,200 assets across the United States. That's essentially every asset 1 megawatt and above. It's about 95 gigawatts of capacity. Some of the things that have come out of that are intuitively obvious when you say them, but there really hasn't been good data on them. So, for example, assets in the Northeast tend to be deteriorating faster than assets in the Southwest. Right? That's pretty intuitive when you say it, but until you actually have the data to look at and actually see the deterioration in some of those assets, it's historically just been kind of something you might surmise, right? Broadly speaking, about 51% of the asset base is what we would consider in good or excellent condition, and about 1.8% is distressed assets, meaning they've got serious issues with either DC power loss, module conditions, or elevated temperatures. That means there's roughly 48% that has some level of distress that needs to be addressed across that asset. Probably one of our fastest growing services right now is glass crack analysis, which I think talks directly to what the other hosts here have mentioned. We see a lot of clients with concerns around crack analysis for a variety of reasons. Some of them performance issues, some of them are safety issues. Like, so when those cracks occur, depending on the nature of the crack and how deep the crack is, during rain events or different types of events like that, you can end up with ground faults that can be serious safety issues for crews on site. So we're doing a lot of glass crack analysis for clients right now. Historically, that was something that you could not do from crewed aircraft. We use crewed aircraft for probably 98% of our inspections in the lower 48 in Canada. While the resolution on that's pretty tight, we're about 2.2 centimeters GSD, which basically means you can see an object that's 2.2 centimeters in resolution from our flights. That's not adequate for most glass crack analysis. It's fine for like a hail strike when you've got essentially a spider web blown up on the panel, but for micro cracks, which is kind of a bigger issue, those micro cracks will not show up even at 2.2 centimeters. So we have a special technique that we use specifically for that. No, we have a special technique that we use to identify those micro cracks.
What about cell cracks then? Can they be picked up by this kind of observation?
The cell cracks I couldn't really talk to. I think we can spot the micro cracks in the glass, right? I think one of the points, and the points have been made here, I think several times, has been the thickness of the glass, right? To go from 3.2 down to 2 millimeters, I think has had a pretty big impact on, no pun intended, on the industry. And I do think that's something that the providers, the module providers, are going to have to look at pretty heavily. This industry, I've been in the industry since 2006, late 2005, and we've kind of internally trained ourselves to cut costs, right? And I do think there's a point of diminishing returns there, and I think the industry is really starting to discover that. It's also true that 3.2 millimeter probably is appropriate in areas where there's a high incidence of hail, whereas a 2 millimeter may be just fine in the Southwest, where hail is almost non-existent. The same thing could probably be said for the region in which you're deploying the asset. So if you're in the Northeast, you're probably going to have to go to heavier equipment, snow loads, extreme thermal cycles, things like that. I live up in the mountains, up by Lake Tahoe, near a place called Truckee. And this last year, we got absolutely hammered with snow. And I can tell you that brand new arrays that were deployed just locally here had pretty severe impacts from just snow loads, because the snow loads are so intense. So you can definitely see the impacts of different regional conditions. And I think historically the market has kind of just assumed everything's going to be the same. So our approach is basically find out what the condition states are in these assets nationally and allow people to baseline those asset conditions. So if there is a hail strike event, or if there is some sort of other event, you can go back and look at the historical imagery and say, how is it conditioned, that asset prior to the event, and what it looked like post-event?
Well, we're talking a lot about the product here, but what about from an EPC or a project developer standpoint? Does the data that you're collecting, market, Zeitview, does that reveal about kind of build quality or something on this kind of installation level?
Yeah, that's a great question. I think intuitively, when you think about it, and as I was mentioning, the market is just, we have this DNA about cost reduction, and at some point there is no magic sauce. The number one challenge in the market is labor, and labor costs are not going down. And when a developer pushes on an EPC to lower their costs, they don't really have any magic, beans to throw about and suddenly drive the cost down. They have to use cheaper components. That's just what it boils down to. So we do think there's probably a correlation between ultimately the condition state of the asset and how the asset holds up, and probably the developer and the partner EPC, right? We don't have data at this point in our data set that would definitively say this is the number one vendor and this is the number 10 vendor or what have you. But we think the data is buried in there. So yeah, we do think there will be some interesting results that will come out of that over time.
It will be interesting to hear. Nicole, at Kilowatt Hour Analytics, how available is data from the field? Performance data and data that may reflect failures in projects?
Yeah, I mean, at Kilowatt Hour, we have a few different channels of getting data. We have a really extensive loss database on the property side, and then we have a lot of production data and some field data, O&M logs from other channels that we have industry partners in our SRP product or our production guarantee product. But it is, I mean, it's a challenge to get, and it's not something that like flows through the typical, at least property insurance channels. It's not something that would really come through a broker necessarily. But even when we do get it, a lot of these, I mean, I could hound on O&M logs and how they're not really standardized. It's difficult to use, right? Like I see Teresa sharing her head, but it's they're hard to use because it's text data and it's written by a field tech, and it's hard. I mean, we're talking using NLP, like natural language processing methods, just to derive what a failure rate of a piece of equipment is in the field. Like that should be something that's very easy to understand and derive from data. And I know a lot of the data standardization initiatives are out there, and like companies like Heliovolta are kind of addressing this, which is great, because then if we have more standardized data, that just makes pulling in the insights just a lot easier. And I mean, I'd echo what Mark was saying too on this idea that there's a correlation between the state of the asset and how well it's maintained versus how well it will hold up. And that's a hypothesis that resonates with us at Kilowatt Hour too. And so that's data that when we do get it, when we're able to pull these insights out, when we're able to say what is a good O&M provider versus a poor O&M provider, or maybe a less so good, I shouldn't say poor, but like not as, the site isn't as maintained as well as maybe it should be. And then same on the EPC, when we're able to make distinctions between those sites, we're able to differentiate price even better and start rewarding, again, resilient behavior or resilient O&M practices or EPC or resilient sites in general, because it reflects, your premium should reflect that reduction in risk that you have by having a more resilient site. And so, the data, while it's a challenge, it's really important, and it's insights that, we like to lump in and take into account when we're looking at a site to see what real risk does it pose. Or is
okay.
it supposed to?
Teresa, did you want to weigh in terms of O&M logs and what you might like to see or information we could use?
That's one of those very hard problems to solve. We've been trying at the national labs for years to figure out ways to get actionable data from the O&M logs. And it's just incredibly difficult. Like if you've ever been out on a field site and take notes and try and capture everything that's going on, it's inevitably done in a pretty non-standard way. So I think this is something we're having some more maybe consolidation or standardization among O&M practitioners, more, kind of like the Zeitview, Heliolytics type perspective on systems, drone analysis. You get a little bit more standard. And then you have to kind of separate, like, what is a module issue, DC health issue from an inverter issue? Where do you have availability problems? Because obviously the first thing that always gets detected is when the electrons stop and the money stop coming, right? So that can be caused by a lot of things, and you got to triage that really quickly. And is that due to something that's recoverable, like you can go reboot the inverter? Is it due to something that's not recoverable, like the modules got smashed? Or is it that the tracker's stuck? You've got to do a lot of quick triage in the field. And a lot of, any sane person, I think, is going to prioritize getting that triage and repair done very, very quickly over taking detailed notes. That's, again, that cost-cutting measure that I don't think any of us can argue with that, even as a scientist who wants that data very badly for my own group and my own efforts. I understand, like, you got to fix it and run. And the note says, I flipped the switch.
Sure. But I can see that you're kind of getting at that bringing together these different data sources will reveal more and more about system health and also failing modes.
Right. PV's getting to this point, and Nicole's much more knowledgeable on this topic than I am, where even at the national labs, we would get a topic on a proposal on like big data analysis of PV, and it would be like 50 systems. You're like, that's not big enough to do what you want to do. And now we are absolutely big enough where we can start to learn at scale. And that should be a tremendous advancement, but it's going to take us some time to figure out how to do it. The most frequent like VIP visitor question we get is, how are you using AI and ML in your stuff? And I think I'll defer to Nicole and Mark on smart ways to use it. But a lot of what we do is like, is that system actually where they say it was? Is it on a tracker, and is the tracker pointing the right way? And that's super important. But that's not the kind of generative AI chat GPT miracle that people are looking for, right?
Mark, do you have something to add to that?
Oh, yeah. I think, what's so funny is we'll have clients say, yeah, we've got a 40 megawatt system located this particular lat long, and we go out to that centroid and we actually overfly every single one of those sites, right? So we're like, yeah, your site's not 40 megawatts, it's like 41.5 or it's 38.5, right? And everybody ends up being shocked. And the reality is that there's just a poor collection of actual asset condition state right now. And we see that literally every site that we fly over. We're getting accurate measurements of the site. It starts with the basics, like how many panels do you actually have at the site, right? A lot of these clients don't actually know that. Well, we've got a complete AI ML team that literally counts panels at the site. So we have a pretty accurate count of every single module now across every one of these assets that we've overflown. And so we feel like we've got the best condition state database, and probably the only condition state database in the world right now for the lower 48. And that's a lot of data to interpret and analyze and derive insights from. But I think to the point that Teresa was making and Nicole, getting data that is unencumbered in the industry has historically been a challenge. And one of the reasons why we did this, what we call the NAS, the North American Solar Scan. Apologies to Canada and Mexico, because it should really be called the Lower 48 Solar Scan. But NAS just came off the tongue a little easier. So, that data set is kind of what enables you to start to really look at sites in, I think, a more constructive way and objective way, and find out where things really are, as opposed to kind of where the industry thinks they are, or what people are touting they might be at, right? A lot of data in the tier ones. I think LONGi is a great example of a company has really rigorous standards around how they produce and how they test, and then how they deliver their modules. Very little data really around actual condition state in the field. Like what has actually happened to the assets once they're deployed. And almost non-existent in terms of global visibility, right, and transparency. So a lot of what we're doing is really focused on that type of outcome.
Okay, Terry, I want to talk about that bit about feeding this kind of field data back into manufacturing. But before I do that, Nicole, would you like to just finish up? Do you have a remark to add to that area that we're discussing?
Yeah, I mean, I'd echo the same stuff that Mark was bringing up. It comes to mind the term that 90% of data science is data cleaning, and I feel like that applies not only on an individual level but on an industry level, right? Where we're kind of in this phase of like we need more data, and it needs to be more standardized. Like AI and ML can overcome a lot of data issues. You could do a lot of data cleaning. You could do a lot of post-processing, all of this, or pre-processing before your algorithms. But I mean, it can only overcome so much. And just imagine like what we could do as an industry as a whole if we had great standardized data that really told the whole story, right? So I guess I'll just add that to the conversation.
Okay, thank you. Now, Terry, manufacturers, how could they potentially use this condition state information from out in the field?
Well, I think when you think about modules, they're designed and they go through a series of qualifications, then they're built, and that is to a standard in a factory. And we spend a lot of time, obviously, at PI Berlin ensuring for our clients that they're built to the standard that's promised. But then you think about every megawatt, hundreds of megawatts, gigawatts that's shipped by a manufacturer, you are reserving for a warranty, right? You have a 25 or 30-year warranty, and so you have to put something on your balance sheet to support those modules. And so what's happening in the field is an essential piece towards what that number should be, right? I mean, if you think about carrying those amounts of money for 25 years, and it's growing, it's not shrinking over time. Essential pieces to that financial analysis are what Nicole and Mark are talking about. It's it's really important that, and obviously anything you can get from the data that can help feed your decision making, both on design and factory operations, I think will only help us as an industry, create really, really reliable and cost-effective products. So I sort of think of it as a triangle between sort of design and fab, deployment and care, and then long-term performance. And so as a manufacturer of the modules, you're going to care about all that, obviously for inverters too, and balance of systems, structures, wiring, et cetera, trackers. But I think particularly for the module makers, where the damage to the modules can be severe, and replacing a module is much more expensive than shipping a module, right? And so I think paying attention to what these findings are will really help manufacturers, I think, hone in on where attention to maybe design change needs to take place, or regional deployment. Again, I'm not necessarily an advocate for that, but if that's the way the industry needs to go, maybe that's the answer.
Well, we've been hearing today about the policy settings, the IRA, and how that's instigating a real boom of domestic manufacturing in the US. Terry, then, some of these manufacturers and nearly all of these facilities will have almost no track record of production. So how should they be going about drawing on this information that we're talking about, what we know in the field, products produced largely elsewhere? How should they be using that to get their products to the quality needed with domestic production?
Well, many of them are not new entrants, right? They either have fabs in other countries or long histories of providing products. So many of them are mapping over sister products, if you will. So they've got a design construct that is similar to something that's been done in large scale before. So I think the data is highly relevant to, again, a sort of a design feedback loop, or a, SBC feedback loop, if you will, on how the choices that you make as a manufacturer and deploy it in your factory will ultimately serve you well in the field. So I think the answer rests in, if you are bringing products to manufacture in these new factories that have any kind of legacy design that you can go back and look at, and look not just at what your shipment data says, but what we're finding at the labs, what we're finding in the field, what the insurance companies are finding. I think all that should feed back into, as you stand your factory up and prepare yourself to be a gigawatt shipper of product out of, new fabs that are being stood up as we speak. I think it just behooves you financially to do that. We, as I said, go in and audit and provide support for these large scale integrators, bankers, financiers, to make sure that what's being built is complying with what they've purchased. That's just one piece of a much bigger, I think, challenge that these manufacturers will have with finding good folks that can train and operate in these highly automated fabs. That has, I think, got a positive and statistical sort of banding of performance as you produce things, this high automation level, but it doesn't substitute for good practice and good data analysis within four walls of a factory. So maybe what really the link is pulling in what we're finding from the field, combining it with what you see in your fab, bringing it back up to your data or to your design criteria and what you see in your testing, really. And if that design loop can continually feed itself, I think we'll get stronger as an industry.
Thank you. Teresa, I'd like to bring you back into the discussion from NREL's perspective. You were talking about big floppy modules. Like, that's quite a descriptive and worrying description rather. We saw these large format modules come onto the market quite quickly. It seems like these innovation cycles are accelerating within the solar industry. What can you tell me about this tension between the need to reduce cost, as Mark said, this imperative, also to innovate and boost power output and bring these new products to market, but then to ensure reliability over the long term? Could it possibly be a case that these innovation cycles are moving too quickly in terms of products coming out into the market?
I mean, it's always hard to say, like, you kind of choke on the words that innovation is moving too quickly, because that's not anything we ever want to say. But product reliability testing takes much more time right now than product development and then the speed of innovation. And so there's a need to better match those cycles. And maybe think about things like when you're doing a really innovative cell technology or you're doing an innovative module design, don't make something that just barely passes a test. You want them to have a bigger, what we would call like a safety factor or design factor as you bring these new innovations in, because the way that the standard tests work is they test for things we've already seen in the field. You know, you make a product, you deploy it in the field, you see something that you shouldn't see, you then do some failure analysis on that, and then you design a test to pick up that exact mechanism, and then you put that out to the industry, and usually you get rid of that exact mechanism in that product. But as we're putting out new products so quickly, and we're putting out all this innovation, and we're making it in all around the world, everybody's scaling up at the same time. And then we've got these project reliability tests that do take longer than the design speed. We've got to figure out how to, you know, move faster. And then as far as the cost cutting thing is this is an argument we have with a lot of people a lot of the time, right? We've got to move away. And in the US, we largely have from this initial cost, this dollar per watt, and cutting that cents per watt cost initially, and that being our only focus, to looking at returns over time, the cost of energy over time, internal rate of return over time, because then you move away from just buying the cheapest module, where you're going to have a higher risk of an early failure, straight up. And so it's a community education effort as well. You know, you may move away from the lowest cost EPC because we do see a correlation between people who have installed more systems and higher quality. And this is intuitively obvious that this should happen. You get more practice, you get better. And I think that's also true of modules. You know, we look at people standing up new factories. We're all going to be competing for materials at the same time. We're going to be competing for expertise. Right now, we're going to be in a hot competition for equipment. Like, who can get manufacturing equipment built on the floor and running really fast? And then who knows how to start up that factory in a way where quality is maintained? And I think that's where, in order to generate, you know, sustainable, renewable electricity that's going to meet our energy transition needs, we probably have to go to a little bit higher design or safety factor in a lot of these new factories and a lot of these new installs than we've been using, so that we have a little room to learn and a little room for error without these catastrophic failures. And then I think we also have to be thinking about where we're installing. If you're installing, you know, in Eastern Colorado, Hale Central, you may do something very different than if you're installing in Tahoe, where you're going to have 4 feet of snow regularly. You know, that's a different kind of load profile, or you're going to have these huge temperature swings in certain places. So, you know, we don't need to worry about humidity. So maybe we would look for a different module. So I think there's a lot of things to consider, and a lot to do on the buyer education side to make sure that we get reliable electricity generation from PV, from all these new factories, which is the ultimate goal.
Yeah, excellent. Yeah, buyer education, that's an interesting point. And of course, policy will also play a role. Over to you, Mark. You know, the ITC, you know, when you've got a CapEx subsidy, there can be a inclination to really look for the most competitive offer on a cost per watt basis. But it could be encouraging the production tax credit. Am I right in understanding that that might actually have a positive impact in terms of that dynamic?
Yeah, I think for sure it will, actually. You know, the ITC has done exactly what we designed it to do from a policy standpoint. It's designed to get capacity deployed, right? And it's done a good job on that. I think the challenge is that if you look at the behavior at the field level, there's frequently a disconnect between, for example, the O&M company and the asset company, because the asset company is really optimizing around their internal rate of return. And I can't tell you how many times I've talked to O&M providers who are completely befuddled when they go to an asset and it's kind of a train wreck, and they go to the asset owner and say, hey, we should fix this. And they go, yeah, how much? And he tells them the price, and they go, no. They don't even there is no conversation. It's like, nope. And they're kind of talking past each other. And I think the PTC can help correct some of that, because the production tax credit is exactly that. It's designed to focus on the production of the asset. I think the reason that disconnect happens now mainly is because, the IRR that's calculated by the asset owner is done inside their own financial pro forma. And that may not be very obvious to, and in fact, is frequently not obvious to the O&M provider. And so the O&M provider doesn't really know what's driving behavior at the asset owner level. The asset owner is making completely rational decisions when they decide to not service an asset. I mean, classic example, like a 15-cent PPA in California that generates around, depending on where you're at in the state, anywhere from $60 to $75 a year in revenue, depending on the era of the plant, right? And maybe a little more on new plants with larger modules. But for an individual module, the question then is, do I really need to take care of that module? Do I need to roll a crew to service that module? And these are people who are already very, very stressed on labor, right? They just don't have enough labor. So do you roll a crew? And truck roll costs, I can't tell you what it is today. I can tell you what it was when I ran O&M at Sun Edison, and I know the costs haven't gone down. We were $800 to $1,500 per truck roll. That's before a single screw or bolt got turned, right? That's just to get the crew to the site. So when you look at it from that perspective, it's very rational as to why the asset owners are like, no, don't do anything. It doesn't really impact their internal rates of return. And that disconnect between the asset owner and the O&M provider is very, very real. We see that on a pretty frequent basis. Now, what I will say is that the production tax credit does mitigate and fix some of that behavior. There's better alignment in terms of what do I actually need to fix and how does it actually impact my returns. And the O&M provider, when they see those defects or there's problems with the plant, they're more in alignment with the asset owner. So I do think there will be some changes, some positive changes with that. We'll see how that rolls out. There's always investors who are going to want to take the ITC and focus more on kind of that short-term yield curve than the ones who are looking at the long-term investment or long-term production of that asset. And there's also differences, of course, between, let's say, utility owners and IPPs, right? Utility owners have other things that they have to take into consideration, voltage support. There's a whole slew of utility oversight objectives they need to meet, and those are very much different than what the internal rate of return is.
Okay, well, potentially a positive development. Unfortunately, we have come to time, but I would like to thank all of our panelists today: Teresa Barnes from NREL, Mark Culpepper from Zeitview, Terry Jester, PI Berlin, and Nicole Thompson from Kilowatt Hour Analytics. Thank you very much for joining Roundtables US. Well, that's it for me today, but we have lots of great sessions coming up. It's been a real pleasure to host another PV Magazine quality roundtable discussion. And while it does appear that there are big challenges, it's encouraging to think that we have some very bright minds working on solutions and increasing our understanding of how we as an industry can continue to construct and operate long-lived assets. My name is Jonathan Gifford. I'm the editor-in-chief of PV Magazine Global. And as I said, there's a lot more to come today on Roundtables US 2023. But for me, that's it. Anne Fischer, the senior editor at PV Magazine USA, back to you in the studio.
Thanks, Jonathan, and thanks also to the session presenters. Our next session will be addressing ramping up grid-scale energy storage. My colleague and fellow editor at PV Magazine USA, Ryan Kennedy, will welcome expert panelists from STEM, Solve Energy, Long Duration Energy Storage Council, and Wood Mackenzie Power and Renewables to discuss energy storage, emerging trends, and overcoming challenges to meet deployment. But first, we'll take a lunch break. I invite all of our virtual attendees to visit our partners' virtual expo booths and network with your colleagues on the platform. We'll see you back here when the program returns at 2:30 p.m. Eastern.